Hey physics, this is the video walkthrough of forces, inertia, and mass. If you want to check your answers on this, I mean, you don't have to because I'm going through the answers, but this comes from the physics classroom, a lesson called Newton's Laws. So if you want to check that out, you are welcome to, and clicking this image is going to take you there also. So, define inertia. Inertia is, I'm going to say inertia means that objects tend to resist a change in motion. Another way to say that is that an object in motion wants to stay in motion in a straight line or in that same trajectory, and an object that is at rest tends to want to stay at rest. So again, thinking about that in terms of our bodies, when we're sitting down chilling, we want to stay sitting down chilling. When we're moving around, it's hard to stop sometimes, or it's hard to change to a different activity. So objects tend to resist a change in motion. I'm going to say inertia means that objects tend to resist a change in motion. So the amount of inertia possessed by an object is dependent solely on its mass. So it doesn't matter what planet you're on, but if it's a bigger object with more stuff in it, like a bus, for example, compared to a bird, the bus is going to have more inertia. It's going to be harder for it to change direction, okay? Or to stop or to start if it's doing one of the opposite things. So here's our first example. Shirley Sheshort and the two bricks. Two bricks are resting on the edge of a lab table. Shirley Sheshort stands on her toes and spots the two bricks. She acquires an intense desire to know which of those two bricks is the most massive, meaning has the most mass. Okay, so that's clicking some bells with inertia that we just talked about. Since Shirley is vertically challenged, she is unable to reach high enough and lift the bricks. However, she can reach high enough to give the bricks a push. So, how is the process of pushing the bricks going to allow Shirley to determine which of the two bricks has the most mass? Thinking about it. Okay, well, so both of those bricks are holding still right now, right? So the brick that is the easiest to move is going to have the least mass, right? And you can think, I mean, just intuitively that makes sense, right? But the reason why that is because it's the amount of force that it takes to overcome inertia. So I'm going to grab my purple color here, purple. Okay. So here, I'll pause this. Okay. So when Shirley Sheshort pushes the two bricks, the most massive, greatest mass brick will take the most force to move. Of course, the bigger brick, it's going to take more force to move it because it's got more inertia. And the least massive brick, the one that has less mass, is going to take less force to move because it's got less inertia to overcome. Okay, so what about if Shirley Sheshort was in space and she was far away from any large objects that are going to affect with gravity? So basically, if she's in a situation where there's no gravity, can she conduct the same study? So I want you to think about that for a second. So there's two answers there. The one answer is that yes, she could definitely still conduct this study in terms of because in space, even though things are going to have a different weight, they're still going to have the same mass. So one of those bricks is going to have more mass and the other one is going to have less mass. And so it's going to take more force to move one and less force to move another to overcome their inertia. However, if we're thinking about the other forces that are involved that come into play with gravity, right? Then it might be kind of difficult to conduct this experiment because we're used to the force of gravity pushing down, the normal force pushing up, and that frictional force having a big impact on the amount of inertia, right? So it would feel different, right? Might take more force, but it would certainly not be like pushing it across a table because there would be no gravity, normal force, or friction. So yes and no there. Let me write that. Okay, so here's the two answers there. Yes, because the amount of inertia that an object has is solely dependent on its mass, and mass is not affected by gravity. So in that way, you could totally do this experiment in space, and it would still work. But it would look a lot different than on Earth, right? Because on Earth, there are a lot of other forces at play. We've got gravity, we've got the normal force that's supporting it, we've got friction between the bricks and the table. So it's going to look and feel really different to conduct this experiment in space, but you'd still get the same results. One is still going to have a lot more mass than the other, so one will still take more force to overcome its inertia. Okay? So the moose. So if a moose were chasing you through the woods, its enormous mass would be very threatening. But if you zigzagged, then its great mass would be to your advantage. Explain why. So again, this is coming back to inertia, right? The moose, since it's so much bigger than you are, has a lot more inertia than you do. So you can change direction pretty quickly. And in the woods, that's also going to be an advantage because there's lots of trees around, and the moose is not going to be able to navigate those trees as well, especially if it's got a big old moose rack, you know? So yeah, the moose has a lot more inertia to overcome than you do is the answer here. The moose has a lot more inertia to overcome because it has so much more mass. So it would take a lot more force for it to change directions to chase you. Okay, so inertia can be best described as, and there's two good answers here, but there's one that's the best. So is inertia the force that keeps objects moving and stationary objects at rest? Is it the willingness of an object to eventually lose its motion? Is it the force that causes all objects to stop? Or is it the tendency of any object to resist change and keep doing whatever it's doing? So, inertia is not the force that causes all objects to stop. That would be like an applied force, that'd be friction, that would be gravity, there's, it could be air resistance even. It's not causing that. It is not the willingness of an object to eventually lose its motion. That would be something like entropy or something. Not inertia though, not inertia. Is it the force that keeps objects moving and stationary objects at rest? That one, I was like, is it that one? It's close. But no, it's not that one, because again, inertia is not doing anything. What it really is doing is inertia is just the tendency of any object to resist change and keep doing whatever it's doing. Okay, so that is our answer there. Underline. Okay. So we're going to rank the objects from least to greatest inertia. Now this one looks tricky, but if you remember the rule about what is the only thing that impacts inertia, then it's pretty easy. So we have mass and velocity for each one of these. So I see a mass of 10 kilograms, velocity of 2 meters per second, mass of 20 kilograms, velocity of 0 meters per second, a mass of 5 kilograms and a velocity of 4 meters per second, a mass of 8 kilograms and velocity of 3 meters per second. I'm going to arrange these real quick, and I want you to see if you can figure out why I arranged them the way that I did. Okay. I'll just do this with the camera on here. Oops, I moved the wrong box. Okay, so what's the pattern here? Why did I arrange it the way that I did? Well, the thing is that inertia doesn't really matter how much velocity you have. It's how much mass you have, right? So, like, I know that this one has the most mass, and so even though it's not going anywhere right now, it's still going to take the most force for me to get it to go anywhere and do anything, right? Whereas this one does not have very much mass. So even though it's going at 4 miles per hour, or meters per second, sorry, even though it's going 4 meters per second, like you can think about like a kid running, right? If they're running at a certain speed, it's still not super hard to grab them and change their direction, right? But if they're 20 kilograms, then it would take a lot more force to stop them and change their direction, right? Same thing with any of these. So the reason why I chose this is because inertia, the amount of inertia is determined solely by the amount of mass. Is determined solely by its mass. Okay, so next one. Draw a free body diagram that shows balanced forces and unbalanced forces. So I'm going to use the example that a student in my first hour gave, and I'm going to draw a cup of water that is just sitting on a table, so all the forces are balanced. And then I'm going to draw a cup of water that shows that's been tipped over, so it has unbalanced forces acting on it. Just a sec. Okay, I'm just going to draw it. So free body diagram is a box. So this is my cup, and there's some arrows. So I have one arrow that's pointing up. I'm going to give it a little bit more thickness. And that is the force of support, or the normal force. And then I'm going to just copy it, and I'm going to say rotate, flip vertically, and so that I have the exact same arrow, same length of arrow, just going the opposite direction. So a cup sits on a table. Nothing is happening to it. Okay, so then actually let's draw this whole situation. I guess I'll have to copy bit by bit. Okay, so then we have this cup that is sitting on the table, and there's still the same amount of normal force. There's still the same amount of gravity. But in this situation, there is an applied force that is pushing it this way off the table. And I'm going to make that applied force pretty long. Okay, so yeah, and then I should label these forces real quick, so I will do that real quick. Okay, so I've added the forces there. We got normal force, force of gravity, normal force, force of gravity, and the applied force that has bumped it off the table. So what is the net force of an object that has balanced forces acting on it? Kind of a trick question, but not really. If the net forces are balanced, then they cancel each other out. So the net force of an object with balanced forces acting on it is 0 newtons. Newtons. There. Okay, last page here. Roller skater net forces. So this is Lily skates a lot. She's super cool. I like to watch her on Instagram. And you can check her out too. She's also on TikTok. So if she has 7 newtons of force pushing her that way, but 3 newtons of force pushing her the other way, then how much net force is there on her? Well, we're going to subtract those forces. We're going to subtract the smaller one from the bigger one because they're working against each other. So she is going to be traveling 4, and I'm saying traveling, but really she has a force of 4 newtons to the right, pushing on her. So then over here, if she's got 6 newtons pushing her that way, but 2 newtons of, let's say, like, I don't know, 2 newtons and then another 10 newtons pushing on her that way. Maybe she's got like the force of her going up at that, but then also the force of a turn, plus also the force of like the wind or something could be those extra 2 newtons. What is going on there? So then we're going to add these two together. So 2 plus 10 is 12. So we have 12 on this side and 6 on this side. So we just do 6, or no, sorry, we do 12 minus 6. So that is going to be 6 newtons to the left because there's more force pushing her from this direction. This one basically it's just canceled out, subtracted from that one. Okay, that's the end of this video. So you are done for today. If you have, once you have this turned in, you're good to go. See ya. And by you're good to go, I mean if you are remote, you're good to go. If you are in person, obviously you just have to chill for a little while. So I'll see you guys on Wednesday. Bye.